Hello students, this is my first class with you and it is an introduction to linear algebra, and today we shall also see definition and some preliminary theorems on linear space. So first, mathematics starts with sets and functions. That's why I am defining what is a set function first. Set you know, assuming that set you know what is a function. A function is an order triple, capital X, comma, capital Y, comma, small f. Function is an order triple x, y, f, consisting of the following: a non-empty set capital X called the domain of the function. Number 2, a non-empty set capital Y called the codomain of the function. A rule or correspondence f, small f, which associates with each element small x of capital X. Important, each element of x of capital X, a unique element, definite element f of x, small f of x, notation is this, of capital Y. The rule associates to every element of capital X a unique or definite element of Y, and in this case f of x is called the image of the element small x under f. If the triple x comma y comma f is a function, then we usually say that f is a function from x to y, denoted by this symbol f colon capital X tends to symbol y, but we read it f is a function from x to y. In fact, only f is not the function, f is the rule of the function. But in practice, we usually say that f is a function from x to y, that x is the domain of f and that y is the codomain of f are all understood. A function is also called a mapping, known to you. If f is a function from capital X to y, then the range of the function f is the set, notation is this, f of capital X is equal to what? It is the set of all images, second bracket f of small x such that x belongs to capital X. It is the set of all images of elements in the domain capital X, and it is a subset of the codomain capital Y, because every fx is an element of capital Y. If f of x equal to y, it may be equal improper subset, that is range equal to codomain, then f is called an onto function. Onto function, that is every element in y has a pre-image. And an onto function is also called a surjective function or a surjection, noun surjection. And we say that f is a function from x onto y. If distinct elements in the domain capital X have distinct images in the codomain Y under the rule f, that is, if x1 not equal to x2 implies f of x1 not equal to f of x2, elements unequal implies images unequal for any x1 x2 in capital X, means in the domain. Or equivalently, the contrapositive of this statement is if f of x1 equal to f of x2 implies x1 equal to x2, that is, if images are equal, then elements must already be equal for any x1 x2 in this capital X. Then f is called a 1-1 function or an injective function or an injection. Different elements have different images. 1-1. Then what is algebraic structure or algebraic system? Let capital A be a non-empty set and A cross A, Cartesian product. This is called Cartesian product of the set A with A itself, A cross A. What is this? This is the set of all ordered pairs of elements, first bracket A comma B, small a comma B. First element from A, second element is also from A. So A cross A is the set of all ordered pairs, first bracket A comma B, of elements of A. Both are elements of A. Then a function star, instead of f, g, h, we are denoting by star. Function star from A cross A to A, Cartesian product A cross A to the set A itself, is called a binary operation or a binary composition. So any function from a cross a to a is called a binary operation or binary composition in the set capital A. Composition in the set or on the set capital A. It is a binary operation in A. And the set capital A together with star. The set capital A together with this binary operation star. That is the ordered pair A comma star, first bracket A comma star. Set A together with star, satisfying some properties. It may say this operation star may satisfy some properties. Is called, this ordered pair is called an algebraic structure or algebraic system. For example, the set capital N, bold N, of all positive integers, natural numbers, together with the usual multiplication cross. Generally, multiplication is denoted by this cross. So, is an algebraic structure because the usual multiplication instead of star, only here it is cross, from n cross n to n is a binary operation. Why? Because product of any two natural number, any two positive integer is again a unique positive integer. That's why it is a function from n cross n to n. So it is a binary operation on capital N or in capital N, binary operation in capital N. Binary operation in capital N in this case. And the image of the ordered pair first bracket a comma b belongs to n cross n under this operation cross means function is denoted by a into b. We read it a into b or a cross b, that is cross first bracket a comma b. Instead of f of a comma b, it is cross a comma b is a cross b, which is a unique member of n. Definite number, product of two natural number, product of two positive integer is a unique positive integer. So capital N is an algebraic structure with respect to this multiplication. Similarly, capital N is also an algebraic structure with respect to usual addition. Sum of two natural number is also a unique natural number. After this point, one should have the knowledge of group, ring, and field to study linear algebra. So you know these things, group, ring, and field. Of course, there are 3 students from PhD that have taken the linear algebra as courseworks. They may not have the idea of group, ring, field. That's why they should study, and I have already provided the materials to them. So now our linear algebra. What is linear algebra in short? Generally speaking, linear algebra is that branch of mathematics which deals with the common properties of algebraic systems, algebraic structures, consisting of a non-empty set together with two binary operations. On the same set, there will be more than one binary operation. So here it is two binary operations. And with a reasonable notion of a linear combination of elements in the set, leading to consideration of system of linear equations, their consistency test, and their solutions. This is in short aim of linear algebra. What is linear algebra? Now, to study linear algebra, matrix plays an important role. So what is a matrix? All of you know what is a matrix, but this is a formal definition, actual definition. You see there is a difference of the definition as you learned earlier. A m by n matrix, we read it m by n, write it m cross n. A m by n matrix over a field capital F. Matrix over a field capital F. This capital F may be the field of real numbers, capital R, or the field of complex numbers, capital C. Generally this, but there may be arbitrary field also. This F may be arbitrary field also. So a m by n matrix over a field F is a function. See, matrix is a function. In mathematics, everything are sets and functions. Mathematics is the study of sets and functions. So a matrix, m by n matrix over a field F is a function. Is a function from the set. What set? The set of all ordered pairs of positive integers. First bracket I comma j, I from 1 to m and j from 1 to n. Set of all ordered pairs of positive integers. First bracket I comma j, I from 1 to n, j from 1 to n. Into this field capital F. Capital A is a function from this set. This is the domain of the function. That's why I have defined the function first. Domain of the function, the set of all ordered pairs. There will be mn pairs, and from this set a function is defined. Capital A is the function, and the images belong to the field capital F. Image of every ordered pair under capital A is a unique element of capital F. That is a matrix. If image of first bracket I comma j, ordered pair I comma j under the function A is the matrix, is small aij belonging to capital F. Aij is a unique element of capital F. Then usually the matrix capital A is described by displaying its entries aij, small a suffix ij, in a rectangular array having m rows and n columns. Capital A is a function, and that function, under that function, images of ordered pairs are there, and that image of ordered pair I comma j is aij notation. It is a unique element of F. I from 1 to m, j from 1 to n. So there are mn elements, and the matrix A, that is the function A, is usually represented by displaying its entries in a rectangular array having m rows and n columns as capital A equal to first bracketed aij, in the suffix we write m by n, m cross n equal to what? First row a11, a12 dot 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 a1n. Second row a21, a22 dot 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 a2n. First suffix denotes row, second suffix denotes column. Dot 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 dot. Continuing, last row is am1, am2 dot 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 amn. So this is representation of matrix A, listing all its entries. Strictly speaking, the rectangular array displayed above this array is not a matrix, but it is a representation of a matrix. The function is the matrix, but in practice we usually say that the above rectangular array is a matrix, and it is a convention only. If we know the array, then we also know the function, and so the convention is justified, because all elements we know means images of all ordered pairs under A we know. That's why we know A. That's why this representation itself is called matrix. This is convention. After this point, one should have the knowledge of all properties of matrices in plural, in detail. There are various types of matrices: addition, subtraction of matrices, and multiplication of matrices, multiplication of a matrix by a scalar, properties, many things, inverse of a matrix, a square matrix, rectangular matrix, etc. One should know. Study linear algebra. So next, we are in a position to define linear space or vector space. So vector space or linear space definition. Let capital F comma plus comma dot, this triple first bracketed F comma plus comma dot, is a field. What is field? We know. And capital V is a non-empty set. And let circulated plus, this symbol circulated plus, is an internal binary operation. Internal binary operation in capital B. That means taking two elements from V, if we use this operation circulated plus, then we get an unique element, new element in B. That's why it is called internal. Two elements in B combined and getting another new unique element in B, internal binary operation in B. And star is an external binary operation in B over F. That is, alpha star x is a unique element of B for any alpha belongs to capital F and x belongs to capital B. Alpha is an element of F field and x is an element of B, non-empty set B, and star is a binary operation. Alpha is not in B but x is in B. So that means in applying the operation between two elements which are not in the same set, alpha is outside B, external to B, but the after operation alpha star x is a unique element of B. That's why it is called external binary operation. By means two, combining two elements. And these two operations, circulated plus and star, are satisfying the following axioms or conditions. Number one, the ordered pair p comma plus circulated plus is an abelian group. That's why I already told we should know what is group. Here it is abelian group. Abelian group means commutative group. That is, the operation is commutative. A circle plus b equal to b circle plus a, commutative. And three more conditions. B plus is an abelian group, means circulated plus is a binary operation in B, and then this operation is associative, and there exists an identity element, and there exists inverse of every element, and also the operation is commutative. So all this make B plus is an abelian group. Number two condition, alpha plus beta bracket star x is equal to alpha star x circulated plus beta star x. See, between alpha and beta, the plus symbol is, it is the plus symbol of the field f. Alpha and beta are elements of the field. So this is the plus. And after operating x with the star and with this alpha and beta, right side the plus is changed to circulated plus, because alpha star x is an element of B and beta star x is an element of B, and between two elements of B the new addition circulated plus should be there. Number three, alpha star x plus y circulated plus y. Here also x and y are elements in B, that's why the operation is circulated plus, and right side is alpha star x circulated plus alpha star y. That is as if left distributive. Here it is in number 2 as if it is right distributive property. Star is right distributive with respect to plus in field. Star is left distributive with respect to plus in the set V. Number 4, alpha dot beta bracket star x. Alpha and beta elements in field, and field in the field there is another operation dot multiplication, alpha dot beta. Star x is alpha star bracket beta star x, right side not dot, because between a element of field and element of B, star should be there. So beta star x is an element of B, and that's why alpha star beta star x, as if associative. Number 5, 1 star x equal to x, where 1 is the unity element in field. In a field there is a unity element, 1 into any element in the field, 1 dot any element in the field is that element. Here it is 1 star x is x. If these 5 conditions are satisfied by star and circulated plus, and also this plus and dot etc., then the composite object V circulated plus star f, composite object, is called a vector space or a linear space. Vector space or linear space. And usually we say that V is a vector space. This is convention. V is a vector space over the field F, and is denoted by B first bracketed F or B suffix F. We call VF. VF is a vector space. So this is definition of linear space or vector space. Note, the elements in V are called vectors and the elements in F are called scalars. If V bracket F, VF is a vector space. Whenever V is a vector space over the field F, VF is a vector space, the elements in V will be called vectors and the elements in F will be called scalars. The operation circulated plus is called vector addition, and the operation star is called scalar multiplication. Alpha is a scalar, x is a vector, so alpha star x, scalar multiplication. In practice, we use the same symbol plus, ordinary plus, to denote vector addition and the addition in the field F. In field also there is addition. Also we write alpha beta and alpha x instead of alpha dot beta and alpha star x respectively. That means circulated plus symbol x circulated plus y we shall not write. We shall write just x plus y. The situation will say whether it is vector addition or addition in the field F. Also alpha dot beta we shall not write. We shall write only alpha beta. Also alpha star x we shall not write. We shall write alpha x. These are convention. Under this convention, the conditions in the definition of vector space looks normal, looks similar, simple. See, V plus is an abelian group. V is an abelian group under plus, under addition. Alpha plus beta into x is alpha x plus beta x, as if our right distributive property of multiplication and addition in real number, similar to that. Alpha into x plus y is alpha x plus alpha y, as if it is left distributive law of multiplication over addition. Alpha beta bracket x is alpha beta x, as if associativity of multiplication and 1x equal to x, as if we know 1 into any real number is that real number, like that, although here x may not be real number, but and 1 may not be the real number 1, it is the unit in the field f, where 1 is the unit in the field f, and alpha beta belongs to f, xy belongs to b, are any elements. So the conditions looks very simple, very natural. These are almost similar to properties of real numbers. Since B plus is an abelian group, B is an abelian group under addition, so it has an additive identity 0 bar, such that x plus 0 bar is x equal to x bar plus 0 bar plus x for all x belongs to B. In a group, identity element should be there. Here operation is addition, so we have denoted it by 0 bar, maybe denoted by 0 also. This element 0 bar is called the 0 vector, which is also usually denoted by 0, simply 0 bar, we shall not give later on. Same as the notation for the 0 element in the field f. In a field, there is also a 0 element, because field is also a group under addition, and it also has a 0 element, identity element, and same symbol 0 may be used for 0 vector and 0 scalar. A situation will say whether it is vector or scalar. So definition of linear space and the conventions written here. Theorem. First theorem. Every field can be regarded as a vector space over any subfield of it. A field is a vector space. Field is a linear space over any subfield of it. Let capital K be a field and F be a subfield of K. Then F is also a field by itself. This is the definition. F is also a field by itself under the same operations as in K. Same operations as in K. In a field, there are two operations restricted to the elements of capital F. When we talk of F, the operation will be restricted to the elements of F. Let us take the vector addition as the addition operation in K, because K is a field, there is addition operation, and the scalar multiplication as the multiplication operation in K, where the first element in the product alpha x is taken from F, there is alpha is from F, and second element that is x from K. Since K is a field, so under the above assumption we see that, see, x is in K, alpha is in F, but alpha is in F means alpha is in also in K, and alpha x is again a unique element in K, obviously, because K is a ring, K is a field. Now K plus is an abelian group, because K is a field, K plus is an abelian group. It is in the definition of field also. Alpha plus beta x is alpha x plus beta x. This is right distributive law in K. Alpha into x plus I is alpha x plus alpha. This is left distributive law in K in a field. A field is also a ring, so left distributive, right distributive properties are true in field or ring. Alpha beta x is alpha beta x by associativity of multiplication in K. 1x is x, where 1 is the unit element in K, and it is also an unit element in F, both. So this is true. These are true for all xi in K and alpha beta in F. And from this, it follows that K is a vector space over F. So very trivial, obvious. Every field is a vector space over any subfield of it. In particular, we can take K equal to F, because a field is a subfield of itself. A set is a subset of itself. A group is a subgroup of itself, like that. So you can take K equal to F. We see that every field is a vector space over itself. That is, for any field F, we can say F bracket F. V bracket F becomes F bracket F. F over F. F is a vector space over itself. So F bracket F is a vector space. Then real and complex vector spaces. Any vector space or linear space, you can say linear space, over the field of real numbers R. The set of all real numbers forms a field under usual addition and multiplication. So any vector space over the field of real numbers R. V is a vector space, and if your field is here R, set of real numbers, real field, then this vector space is called a real vector space. And any vector space or any linear space over the field of complex numbers, capital C, bold C, is called a complex vector space. So depending on the field, we say that the vector space is real vector space or complex vector space. A vector space over the real field is real vector space over the complex field is complex vector space. Very natural. For example, R square, R cross R, capital R cross R, Cartesian product, xy plane, Euclidean plane, set of all ordered pairs, first bracket x comma y, where x, y are real numbers, is a vector space over the field of real numbers R under the operations first bracket x1 y1 plus x2 y2 equal to x1 plus x2 comma y1 plus y2 means point wise, component wise addition. Alpha x1 comma y1 is alpha x1 comma alpha y1. Alpha goes inside. Point wise multiplication. Where x1, y1, x2, y2 are in R and alpha also in R field. That is R square bracket R. V bracket F here is R square bracket R is a vector space. We shall see it in case of R to the power n or F to the power n later. Now we are just citing the example. R square bracket R is a vector space and it is a real vector space because it is over R. Similarly, C square, complex cross C cross C, complex. C is the set of all complex numbers. Cartesian products of C itself, C cross C, is the ordered pair of all complex numbers x comma y, where x, y are complex, is a vector space over the field of complex number C, and so it is a complex vector space. The operations in C square bracket C are same as in R square bracket R, means same. Only x1, y1, x2, y2 you have to take from complex field C and alpha from C. Now another theorem. Every complex vector space is a real vector space. Looks odd. Every complex vector space is a real vector space, but this is true. Generally, we know every real number is also a complex number, but here it is every complex vector space is a real vector space. Looks like reversed, but not reversed. See, let V is a complex vector space, that is V is a vector space over the field of complex numbers C, and therefore V plus is an abelian group. Alpha plus beta x is alpha x plus beta x, alpha x plus y is alpha x plus alpha y, alpha beta x is alpha beta x, 1x is x. Conditions we have written for all x, y in V and alpha beta in C. These conditions are satisfied by all x, y in V and all scalars alpha beta in the set of all complex numbers, complex field. Now, since every real number is also a complex number, we know every real number is also a complex number. So, if I take alpha beta from R, alpha beta belongs to R, then surely alpha beta belongs to C. Every real number is also a complex number. And therefore, the above conditions, these 5 conditions, hold 1 to 5 hold or satisfied for all alpha beta in R. If I take alpha beta from R, automatically I can say that they are also in C, and therefore the conditions are true for real scalars also, and x, y belongs to B already, and hence B is also a vector space over the field of real numbers R. That is, B is also a real vector space. So every complex vector space is a real vector space space because reason is every real number is a complex number. This is the sole reason. The converse of the above proposition is not true. That is, a real vector space may not be a complex vector space. For example, we consider the real vector space R square bracket R. We have seen it, it is a real vector space in which we see that B is equal to, suppose small b is equal to first bracket 1 comma 2, ordered pair 1 comma 2, it is in R square, xy plane. And if alpha is 2 plus thrice I, complex number, then alpha b is alpha into 1 comma 2 bracket, alpha goes inside alpha 2 alpha, but alpha is 2 plus 3i, so it is 2 plus 3i and 2 alpha means 4 plus 6i, but this is complex comma complex, this does not belong to R square. This is not ordered pair of real numbers, so does not belong to R square. Therefore, R square is not a complex vector space. This R square is not closed under the scalar multiplication. That's why R square is not a complex vector space, not a vector space over capital C. So, justified. Next theorem. Let V is a vector space over the field F, and let 0 bar and 0 denote 0 vector and 0 scalar respectively. Initially, let us denote by different symbols 0 bar and 0, 0 vector and 0 scalar. Finally, we shall remove this bar also. Then, first result is alpha into 0 bar is 0 bar. Although there is star, we are not writing star. Actually, it is alpha star 0 bar. So, alpha into 0 bar is 0 bar. 0 into x, here it is actually dot. 0 into x, here alpha star. And here it is 0, x is 0 bar. This 0 is scalar 0. So there will be also star. 0 star x is 0 bar. But star we are not giving. Already told. Roman 3 minus alpha x is alpha into minus x equal to minus alpha x. This bracket may not be given also. Just minus alpha x. minus 1x is minus x. Alpha minus beta x is alpha x minus beta x. Alpha into x minus y is alpha x minus alpha y, means distributive with respect to subtraction also. Alpha x 0 bar implies alpha 0 or x equal to 0 bar. Scalar into vector is 0 vector. Then either the scalar is 0 or vector is 0. For all alpha beta in F and xy in B. So let us see the formal proof. Looks like trivial, obvious, but we shall have to give the proof, formal proof, rigorous proof. Since 0 bar is the additive identity in V, V is a vector space, so V plus is an abelian group, so it will have identity element that is 0 bar. And 0 vector is actually additive identity in V. So 0 bar plus 0 bar is 0 bar. Therefore, if we multiply by alpha, alpha into 0 bar plus 0 bar is alpha into 0 bar. Star we are not giving, just into. Implies alpha 0 bar plus alpha 0 bar distributive equal to 0 bar plus alpha 0 bar. See, in the right side one 0 bar we have added extra. Why? Since 0 bar plus alpha into 0 bar is alpha into 0 bar, because 0 bar is the additive identity, we can add it. Now, by right cancellation law, alpha 0 bar can be cancelled from the right. So we get alpha 0 bar is 0 bar. By right cancellation law in V plus, in a group cancellation law holds V plus. V is a vector space, means V plus is an abelian group. So cancellation law with respect to addition holds. So we can cancel this alpha 0 bar and alpha 0 bar and ultimately got alpha 0 bar equal to 0 bar. So proved first one. Number 2, since 0 is additive identity in the field F, field is also a group under addition. So 0 plus 0 is 0. Now 0 plus 0 into x, star we are not giving. 0 plus 0 into x is 0x, right side 0x. But here it is distributive, 0x plus 0x equal to 1 0 bar we have added extra in the right side, because 0 bar is the additive identity, we can add 0 bar plus 0x will be again 0x. Now by right cancellation law we cancel here also 0x. This 0x we can cancel, mentioned by right cancellation law in V plus, because 0x is an element in V. So 0x equal to 0 bar. Number 3, we have minus alpha plus alpha equal to 0. Therefore minus alpha plus alpha bracket into x means star we are not giving is equal to 0x. Now distributive minus alpha x plus alpha x equal to 0 bar, because 0x equal to 0 bar already proved. Now therefore minus alpha x plus alpha x is 0 bar equal to alpha x plus minus alpha x. Why? Because B plus is an abelian group, so minus alpha into x can be taken to the right side also. A plus B equal to B plus A, like this, abelian, commutative. So, and if this line is true, then we know that this minus alpha x is called additive inverse of alpha x. So therefore minus alpha x is additive inverse of alpha x. Therefore minus alpha x into x is the inverse of alpha x, additive inverse of minus alpha x. Again minus x plus x is 0 bar, so multiply by alpha both sides. So alpha into minus x plus x is alpha into 0 bar. Now it is distributive, alpha x minus x plus alpha x equal to 0 bar. Alpha into 0 bar is 0 bar, already proved. And therefore alpha into minus x plus alpha x is 0 bar, and we can write it alpha x plus alpha into minus x, because commutative again. So these two terms we have interchanged and got this. And if this happens, then this alpha into minus x is called additive inverse of alpha x. So we have written alpha minus x is additive inverse of alpha x. Therefore alpha minus x is minus alpha x. And from these two the result follows. Alpha into minus x is minus alpha x, and minus alpha into x is also minus alpha x. Next, number 4. We have minus 1 plus 1 0. So minus 1 plus 1 bracket into x is 0x, implies minus 1x plus 1x is 0 bar, but 1x is 1. 1 star x equal to x star we are not giving, so 1x is x, unit element in the field F1, that's why. So minus 1x plus x is 0 bar, and by commutative property of addition we can write x plus minus 1 into x. So if this line happens, then sum of two elements 0 element, that's the one is the additive inverse of the other. So minus 1x is the additive inverse of x, therefore minus 1x is minus x. Direct proof. Or indirectly we know minus alpha x is minus alpha x for all alpha. So in particular we can take alpha equal to 1, unity in F, and get minus 1x is minus 1x, but 1x is x, so minus x. Number 5, alpha minus beta x is alpha plus minus beta x. So this is the meaning of actually subtraction, alpha plus minus beta of x. Now by distributive property, that is in the definition of vector space, alpha x plus minus beta into x, but minus beta into x is minus beta x. We have already proved here. Minus alpha into x, minus alpha into x, minus alpha into x is minus alpha x. Here of course you may not give the bracket. If you do not give the bracket, this is convention, it can be only minus alpha x. So if it is beta, it will be minus beta x, that we have used here. Minus beta x is minus beta x. So true. Similarly, alpha into x minus y is alpha into x plus minus y. Again, by distributive or by definition of that vector space condition, alpha x plus alpha into minus y. But alpha into minus y is again minus alpha y. So got. Number 7. Let alpha x 0 bar. Now we have to prove that either alpha is 0 or x is 0 bar. Where alpha is in field F and x is in vector space B. If alpha is 0, then we have nothing to prove. Our aim is to prove either alpha 0 or x 0 bar. So if alpha is 0, we stop. If alpha not 0, then alpha inverse belongs to F. This is the from definition of field. In F, what is a field? A field is a commutative ring with unity in which every non-zero element has its multiplicative inverse. So alpha is a non-zero element in F, so its multiplicative inverse alpha inverse belongs to F, satisfying alpha alpha inverse equal to 1 equal to alpha inverse alpha. 1 is unity element in the field. So if alpha not 0, we are getting alpha inverse, satisfying this condition. Now alpha x 0 bar implies multiply both sides by alpha inverse, and by associativity alpha inverse alpha is 1, so 1x, and right side is, we know scalar into 0 vector is 0 vector, already proved. Alpha into 0 bar is 0 bar means alpha inverse into 0 bar is also 0 bar because it is a scalar. So 1x equal to 0 bar means x equal to 0 bar. So what we have seen, if alpha 0 we stop, and if alpha not 0 we have got x 0 bar. Therefore alpha x 0 bar implies either alpha 0 or x is 0 bar. And this property contrapositive is given in this example, just contrapositive statement, another way of telling this. What we have proved, alpha x 0 bar if means alpha 0 or x 0 bar. So if alpha not 0 and x not 0 bar, then product cannot be 0, that is there. Let B is a linear space or vector space, and let B is a non-zero vector in capital B and alpha is a non-zero scalar in F, then prove that alpha B not equal to 0. Alpha not 0, B not 0, then alpha B not 0. So given alpha belongs to F, B belongs to B with alpha not 0, B not 0. Therefore alpha inverse belongs to F, such that alpha inverse 1 equal to alpha inverse alpha. If alpha be 0, our aim is to show alpha be not 0. If alpha be 0, then we can multiply both sides by alpha inverse and get alpha inverse alpha B equal to alpha inverse 0 is 0. Here we are not giving bar, means 0 vector and 0 scalar denoting the by the same symbol. So 1b is 0 implies b 0, a contradiction because b is not 0. Therefore alpha b not 0. So thank you for today, and in the next class we shall have examples of linear space, how to show a given set will be a vector space or linear space under given operations. Thank you.